just have a handful of slides to go through just so you understand the overall architecture and some of the terminology we use when talking about CFD. And then the more interesting part is to go over to Rhino and Orca in the Rhino environment and create a simulation just to show you how easy the process is. So the first question that many people ask is, why did we create Orca3D Marine CFD? Well, we've been creating software for naval architects for many years, and in Orca itself, we've incorporated two of the most popular empirical or semi-empirical methods for predicting hydrodynamic performance of boats and ships: the Savitsky method for planing hulls and the Holtrip and Menin method for displacement hulls. And those two methods are very popular and very robust and fast, and a lot of people use those for early stage design, either directly or together with some correlation or adjustment factors based on historical data from past designs. But while those two methods are extremely powerful, they also have substantial limitations. Really, when you're applying those methods, you're limited to the baseline assumptions that are incorporated into those methods. So for example, a lot of users who are doing new planing hull designs are interested in things like stepped hulls, or they have spray rails, lifting strakes on the bottoms of their hulls to improve performance. But Savitsky's method did not have any of those features, so it's hard to accurately predict performance for those types of designs. Secondly, it's very difficult to be innovative when you're basing your performance predictions on semi-empirical approaches, because by definition, the semi-empirical approaches are based on known behaviors from existing designs or models. So it's very hard to be innovative with those two approaches. So with that in mind, we created Orca Marine CFD, first of all, to allow you to improve the performance of your design by being able to accurately assess the impacts of things like tunnels for your propellers, hull steps, stern flaps or wedges, thrusters, etc. But also to encourage innovation by allowing you to have a high fidelity way of analyzing the performance of your design early in the design. Most importantly, however, to many is the fact that you can reduce the cost of your design and the risk associated with the design by identifying potential issues, design flaws or performance issues before you build the boat and have to fix the boat. So being able to analyze and identify those issues early on is very beneficial. So when we talk about Orca3D Marine CFD, we're really talking about three products that work together as a system. The first is the Rhinoceros General Purpose Modeling Program, which I'm assuming you're familiar with. Rhino 3D, many people call it, or Rhino, is a very powerful and easy to use CAD modeling program. The developers of Rhino, McNeil and Associates, have opened up the platform so that third-party developers like us can add our functionality through plugins. So we've built a plugin to Rhino called Orca3D. It's a marine plugin that has functionality for building your design and for analyzing it. One of the most used pieces of functionality is our hydrostatics and stability engine, where you can analyze, for example, how your boat will float for a given weight and center of gravity, or determine things like righting arms to assess the intact stability of your vessel. In addition, though, to those pieces of functionality, we've incorporated the interface to the CFD program into Orca3D. The CFD, the Computational Fluid Dynamics program that we use in this system, is called Cimerix MP, multi-purpose, and it's from a company named Cimerix that is located on the west coast of the US near Seattle, Washington. That is a standalone program, so it's not running inside of Rhino like Orca does. It runs as a standalone program. However, Orca sets up the simulation automatically through files. And then when you open Cimerix, all you have to do is click the run or the start button to start the simulation. Now, you do have to learn how to use the user interface in Cimerix in order to monitor the simulation, to get some data out of the simulation, to determine if your simulation has converged. But you don't have to really know a lot of details about CFD. So Orca Marine CFD incorporates Rhino, Orca, and Cimerix MP. The real key to making Orca Marine CFD usable or practical for the engineer, the designer, the naval architect is several features that are shown here. The first of all, the fact that it can run relatively fast. Now, when I say fast, I don't mean as fast as a Savitsky analysis or an empirical approach. I mean relative to other CFD tools. So that means depending on your hardware that you're running on, you can finish a simulation in as little as a couple of hours to maybe 10 to 12, 14-hour time frame overnight, depending on your hardware. We list our minimum hardware requirements for Orca Marine CFD on our website, but the key things to realize are that CFD is fairly memory intensive, so you want to make sure you have at least a minimum of 16 gigabytes of RAM to do the evaluation. Later on, you might even find that you need more RAM than 16, maybe 32 gigabytes, which is what I have on my laptop. But the other thing to keep in mind is the faster your processor, the more cores you have. CPUs these days have multiple cores, and because CFD can be a heavily parallelized program, meaning it can be distributed among multiple cores, that means that if you have more cores on your computer, the CFD program can take advantage of that and run faster. The real trick, though, to making CFD approachable and practical for the naval architect and the designer or the engineer is something called a template architecture. So Cimerix MP, the CFD program, is a general purpose CFD program, meaning it's used not only for marine problems, but it's also used in industries like the automotive industry. It's used for analyzing flow inside of pumps, heat transfer in the electronics industry. So there's many uses of it. In order to make it approachable or useful for a particular problem, you have to set a lot of settings for that general purpose tool. The template architecture allows that setup of the simulation to be automated. So there are templates for different industries. And of course, there's one for the marine industry. We call it the marine template. So the marine template handles a lot of the setup, things like the automated mesh generation, picking the length of the simulation, how many time steps to break the simulation up into, and many other things as well. That's really the technology that encompasses all the knowledge and expertise of the marine CFD expert so that you don't have to become an expert. Lastly, one thing that makes this tool unique from some others is that we have affordable and flexible licensing options. So as we'll discuss towards the end of the simulation, we have both full-time licenses and intermittent licenses. We'll talk a little bit more about those licensing options at the end of the simulation. Just by way of background, Orca3D was first released over 10 years ago in 2008, and we now have over 2,500 users, including navies, yacht builders, shipyards, universities, etc. And Cimerix MP was first released in 2005. We began to partner with them to sell Orca Marine CFD in 2017. So both of these tools have been in the industry for quite a while, and they both have a pretty significant footprint in the marine industry. Just so you understand what's happening with Orca Marine CFD, I have this data flow model here showing you the information that gets passed from Rhino and Orca into the CFD program when you run the command that we're going to show you in the demonstration. So there's really one command that you run that sets up the simulation and launches it. In doing so, it gathers some input information from the user and passes that information along with your model over to the CFD program. And here's a list of the information that gets transferred. So, of course, most importantly is your geometry. So the model in your Rhino will be automatically meshed, and that mesh representation of your CAD geometry gets sent over to Cimerix. But in addition to the geometry, we have things like the mass properties and the static equilibrium attitude. So we assume your vessel's floating, and for a floating vessel, of course, the weight and center of gravity is related to the condition, sinkage, trim, and heel, that the vessel floats at. We use the Orca hydrostatics engine to figure that information out and pass both pieces of information over to the CFD program for simulation. Also, properties of your fluid. We need to know whether you're running in freshwater or seawater or something in between. We need to know things like your model units and orientation, the speed that you want to analyze, and then some additional information that helps the marine template do its job most effectively. Mainly what we're asking you to tell us is what type of hull are you analyzing? Is it a planing hull, a displacement hull, maybe a high speed displacement? Some people call that semi-planing hull. By telling us that information, we're able to optimize the setup of the simulation and the meshing done for the simulation. In addition to the hull type, we need to know the analysis type. There's currently two types of analyses that are part of the standard version of Orca Marine CFD. The first type we call a resistance analysis. Sometimes we also call that a towed analysis. And the second type is a powered analysis, and sometimes we call that a self-propelled simulation. And in the next slide, I'm going to talk about the differences and similarities between the two. So here you see a model that we're setting up for a resistance simulation. With the resistance simulation, the main input driving the simulation is the speed that you want to tow the model at. There's an unlimited amount of towing thrust or force that can be applied to the simulation to reach that speed. So there's no limit to the force that can be applied. We will reach the speed that you request. It's very similar to a model scale towing tank test. If you're familiar with those or have ever observed one of those, you have a towing tank with a model of the vessel of interest in the tank and a towing carriage that tows the model down the tank at your specified speed. Normally in those tests, what you measure are the attitude of the vessel as well as the force required to drag or tow the vessel down the model tank at that speed. And it's a very similar thing in Orca Marine CFD. With the resistance simulation, you specify your model speed in addition to the other information that I talked about in the last slide. But you specify your model speed and the model gets towed by default at the center of gravity, although you can adjust that vertically, but by default it's at the center of gravity. The vessel is free to move up and down during the simulation. We call that heave, and it's free to rotate about a transverse axis. We call that pitch. So the vessel will respond to the forces that are applied to it much like the real vessel would. And in the end, when everything steadies out, it reaches a steady state condition, and you can extract your model attitude and your forces, principally the drag of your model. So this type of simulation is very good for optimizing your design, maybe adjusting your hull form in order to figure out how to make the drag the smallest, adding lifting strakes or spray rails for a high-speed planing boat, or if you have to have a tunnel because it's a very shallow water boat, you want to determine how to design that tunnel so it has the least negative impact on the drag. You can look at different tunnel shapes, for example, and find the shape that is optimum from a drag point of view. The second type of simulation, we call that a powered Sometimes we call it self-propelled simulation. That is very similar to resistance, except that the force that's propelling the vessel in the simulation is not a towed thrust that's unlimited, it's a propeller thrust. So we have to have some approximate estimation of what your propeller looks like and what its performance is like in order to perform this type of simulation. In this simulation, you don't know exactly what speed your vessel will reach. What you know is what propellers you have. You could have more than one, you can have one. What RPM the propeller is turning at, and we determine the thrust that's produced by that propeller based on some performance characteristics for the propeller that you've provided ahead of time. And the vessel will just accelerate up to the speed where the thrust and the drag force are equal but opposite and reaches an equilibrium. Again, the model's free to heave up and down, and it's free to pitch in this simulation as well. It's just that it's going to reach a speed that represents the speed associated with the RPM and thrust from that propeller. So because there is a simplified model of the propeller, and I should note in this simulation, the propeller model is not the actual geometry of the propeller blades, because that's very hard to get. We use something called an actuator disc or a momentum disc to represent the propeller. And that disc requires as its definition things like the gross geometry of the propeller, for example, its diameter, its location, but it also requires information that allows us to compute the thrust. If you have the thrust characteristics in the form of an open water curve, we'll use that. If not, we can use one of the standard series propellers, such as the B series or Gone Burl, to compute an open water performance curve for the propeller based on some very simple information, such as the number of blades, the propeller pitch, and the propeller expanded area ratio. So with these two types of simulations, and you can see one in the lower right-hand corner running, the model starts at 0 speed, accelerates up to either the towed target speed or the equilibrium speed for the propeller RPM that you specified. And then once it's reached that steady state condition, you're ready to extract data from the simulation. You can see in this simulation that's here, shown here, we model both the water and the air in all of our simulations that we create with Orca CFD. So you can get the heave and pitch prediction, you can get streamlines in air and water, which can be very useful, for example, for aligning your appendages to minimize drag. You can predict porpoising behavior, which is a dynamic pitch instability. Porpoising is an instability, so you can try to avoid that by analyzing whether your model will porpoise. You can extract forces and moments from both the entire model as well as individual pieces of the model to help you size other parts of your design. And you can even do things like propeller wake studies. So there's a lot you can do with just these two types of simulations. Okay, this is the final slide before we go over to the demonstration. This is just very important reference information that you might use during your use of your license. The first place to find help information is in the Orca help file. Cimerix has a help file as well as Orca, but the Cimerix help file tends to be more general CFD help than it is specific marine help. The marine specific help is in the Orca help file under the topic shown here called Orca3D Marine CFD. So as you evaluate and come up with questions, I would encourage you to look first in the Orca help file to see if your question might be answered. If you're not able to obtain an answer, you can send an email to this email address, support@orca3d.com. Sometimes we might ask to do a little online meeting so we can show you something. Sometimes it's just easier to respond directly to the email. We also have a number of frequently asked questions on our Orca knowledge base, on our website, and then we have a YouTube channel where you can view videos to see how certain aspects of Orca Marine CFD work. So with that overview, I now wanted to go over to Orca and Rhino to go through a brief demonstration of the process, just to show you how easy the process is. This is a sample model
that we use for our demonstrations, we like to use it, it's a planing hull clearly, but we like to use it because it has a number of interesting features, like our tunnels where the propellers are located. It has some appendages like rudders, lifting strake, has a little rub rail on the side. So it has some modicum of definition on the top side above the water surface as well. So it's really up to you how much you want to model above the water surface. You don't have to have a pilot house or a superstructure like this if you don't want to, but if you do include it, it will be incorporated into the simulation automatically, and its effect on the performance of the vessel will also be included. The only requirement for the geometry to use it in Orca Marine CFD is that it consists of one or more closed volumes. So when I select this geometry and look in the Rhino object properties dialog, you can see it says it's a closed solid polysurface. That closed is the key there because that means there's no open or what Rhino calls naked edges. You're not allowed to have any naked edges. It's got to be a watertight volume. Couple of points to make. It can be a watertight surface, a watertight polysurface, or a watertight mesh. Those are all valid geometric forms for Orca Marine CFD. And the second point to make is that you can have multiple volumes that aren't attached. So for example, you could do a multi-hull like a catamaran where you've designed the two hulls for the catamaran, but haven't yet designed the geometry that connects the two hulls. You could still perform an Orca CFD analysis with those two hulls, even if they weren't geometrically connected. In the simulation, those two hulls would be treated as if they were rigidly attached, regardless of there not being any physical connection between the two. So just point of interest to make there. Normally, before we run this command that I referred to earlier to create the CFD simulation, we first go into the global settings or global properties of Orca3D just to check a couple of items. The first item is my model orientation. One of the things we purposefully do in Orca is we allow the user to orient their model in any way they want. Some people like to have the model with X longitudinal, some may have Y longitudinal. There's really no requirement for Orca. We just ask that you tell us how your model is oriented so we know. So this is the fields where you tell us how your model is oriented, and the way you do that is you tell us what direction in Rhino corresponds to forward and what direction in Rhino corresponds to up. Once you've told us those two pieces of information, we now know which way, for example, to propel the model when you're doing a towed run. Otherwise, we would have to guess and we might end up choosing the wrong direction. So this is where you tell us that. The other thing to look at in the global settings or global preferences for Orca is under the hydrostatics tab. And this is where you set your fluid properties. So typically and historically, this is where we set the hydrostatics fluid specifically for stability and hydrostatics calculations, but now we're also using this for hydrodynamic calculations for Orca Marine CFD. So you'll want to consider that before you start the command for running the simulation. There's many other settings here, but those are the two principal ones of interest for your purposes. To start the command, we go under Orca3D Speed Power Marine CFD Analysis. This is the command that will interface to the CFD program from Cimerix called Cimerix MP. When I run this command, it first asks me to select the geometry that I want to use. And of course, in this case, I only have one piece of geometry. It's one big closed solid polysurface. And when I accept that, it asks me for various pieces of information. The first part is about getting the weight and center of gravity and the static flotation plane associated with that weight and center of gravity. Both of those are necessary for running the CFD analysis. Because we have a hydrostatics engine built into Orca that can compute the float plane for a weight and center, or conversely, can compute the weight and center for a float plane, we allow you to input either one. Whatever one you want to input, whichever one you know for the simulation, for the study that you're performing, you would input. In this specific example today, I'm going to assume what we know is the weight of the vessel through a weight estimate. So I'm going to assume the vessel weighs 10,000 pounds, and our weight estimate gave us an LCG, a TCG, and a VCG. So I'll input those. And when I click the yellow float button, the vessel is floated, and you get a sinkage, trim, and heel value corresponding to the weight and center of gravity. And the way that I know these two sets of values are in sync, so to speak, or synchronized, is that this button is green, meaning it's found the balance between the weight, center of gravity input, and the sinkage, trim, and heel. Because the simulations that we're running are dynamic, meaning the vessel is moving, we must have an estimate of the moments of inertia of the vessel. That being said, since the simulations are really steady state in the sense that they're moving during an initial period of the simulation, but eventually they reach a more or less steady state simulation, the actual values that we use for the inertias just have to be reasonable values. They don't have to be that accurate, because in the end, the vessel isn't moving very much. It reaches a steady state heave and pitch, for example, and at that point, the moments of inertia aren't really having much of an effect. So we just use these check boxes here, which apply naval architectural rules of thumb to estimate the moments of inertia, and we don't change it from that hardly ever. There's a few specific cases where you might need to change those values, but by and large, for the base analyses that we do in Orca Marine CFD, you do not need to change these values. Next, we need the name of the project. This project name, whatever you type in here, will be the names of the files that get created by Orca in order to run the CFD simulation. This name defaults to the name of your Rhino file, but it can be changed. We also need the name of a path to place the files that we're going to create. And again, the default path is where your Rhino file is. I'm going to create a subfolder, so it's going to place the files that it's going to create in this path, and it's going to call the files this name with different things appended to the end of it. Here's where you choose the type of run. You remember there were two types of simulations you could perform: the resistance, which we also called the towed run, or the powering, which we also called the self-propelled run. Remember, the difference, the main difference, is that in a powering run, you have a model, a representation of the propellers, whereas in the resistance run, you don't. So as a result of that, if I select powering here, I get a new tab to define my propellers. Because if I'm going to have a model of my propellers, I need to have some way of inputting that information. But when I choose resistance, you don't need the propellers because they're not in the model. So we're going to start with the demo with a resistance simulation. Next, I need to choose a hull type for the simulation. And when you drop this down, you get your list of hull types. This is clearly a planing hull, but you should base that on your particular design. If it's a displacement hull, if it's a large, low speed or moderate speed ship, it's probably a displacement hull. Some boats or ships can run in a region that is what some people might call semi-displacement or semi-planing, and that's really what the high speed displacement is intended to represent. So we're going to use planing hull for this particular model because this clearly is a planing hull, as I showed you earlier when I was looking at the features. We have to give it a speed. So I'm just going to choose a speed, say, of 25 knots. Okay, so we're going to run a 25 knot analysis. And the last thing we have to do before we run the simulation is we have to attribute faces, this other yellow button down here. So when I click on that, what you see is you see a form here with 3 different face types. You may have 4 in yours. Hull faces, which are red, deck faces are green, and transom faces are blue. And by default, everything's red because we haven't done anything yet, and the model just assumes everything is a hull face by default. But what we're going to do is provide some additional information so that the marine template can do its job more effectively. So I'm going to click on deck, and I'm going to select those faces in my model, which I consider deck faces. These green faces, which are now considered deck faces, the main feature associated with them as far as the CFD simulation goes is that they're always on the air phase of the problem. They're not being dragged around in the water, they're being towed in air. And because air is so much less dense than water, the forces due to the air drag are typically many times less than the forces due to the water drag. As a result, we can do some optimization to the meshing so that we don't have so many cells in our mesh on the air side. And the value or the reason we do that is to make your simulation run faster, because why wait for a long time to get very detailed air drag results when the air drag may only be 1 or 2% of the total drag? You could be off by 10% on that and hardly have any effect on your overall performance prediction. So part of this face attribution process is identifying deck faces that we can mesh more coarsely or with fewer cells. A second use of this face attribution process is to denote faces that you might want to extract forces and moments for after you've run the simulation. By default, when you run the simulation, you'll get the total drag, you'll get the air drag, you'll get the water drag. But say you were doing analysis of your design in order to optimize an appendage like your rudders. One way to do that would be to analyze different rudder shapes and measure the drag on those different rudder shapes. You couldn't do that with the current setup because the rudders are red like the hull, so that means they're part of the hull as far as the CFD analysis is concerned. In order to be able to analyze the rudder drag separately from the hull drag, we have to give them their own face type. So I'm going to right click in here and add a new face type called rudders. And then I'm going to select the surfaces associated with the rudders. And you can see they've got their own color now, meaning they have their own rudder face type. Again, what this will do in terms of your simulation, it will allow you to measure or extract the forces and moments applied to the rudders separately from the forces and moments on the rest of the problem, which can be very useful in certain design scenarios. So those are the two types of face attributes we typically apply, and you can see the buttons turn green indicating that we've done our face attribution now. So that's really all you need to do to run the simulation. The next step is to click the Run Simulation button, and when you do that, it'll pop up a little dialog allowing you to launch the simulation. So this feature here allows me to start the CFD simulation from the Rhino user interface. I want to point out that Cimerix MP is a Windows application. It's a standalone application like I pointed out earlier in the presentation. So you're free to start it up directly like you would any other Windows desktop application. The ability to launch Cimerix from Rhino and Orca is really just a convenience. So what I'm going to do is hit the launch button. And what that'll do is it'll start up the Cimerix MP CFD program, and it'll automatically start loading the information about your model into Cimerix. So like I mentioned earlier, things like the geometry, the mass properties, the static equilibrium attitude, the fluid properties, model units and orientation, all of those pieces of information are getting loaded right now. And what it's doing is it's meshing the fluid domain. Typically for CFD analysis, meshing of the fluid domain is one of the more time-consuming and difficult parts of the problem. And part of that is because while you may be familiar with meshing in a CAD program like Rhino, meshing for CFD is really an order of magnitude more complicated. It's not a 2D problem like CAD meshing, surface meshing, where you're breaking up a surface into little quads and tris. Here, you're breaking up a fluid volume into little, what we call cells. You can think of them as cubes or bricks, blocks of fluid. We're breaking a volume into smaller volumes in order to be able to solve the problem. Okay, so we're now in Cimerix CFD, and right out of the box, we're able to hit
the start button to start the analysis. So I'm going to do that just to show you that there's no adjustments that need to be made. Also, it'll let the simulation make some progress so that you can see how the program runs on my computer. Just by way of background information, I'm running this on a 3.5-year-old laptop computer with a 7th generation i7 processor from Intel. It has 4 cores. So it's practical to run on this. Obviously, if you have a faster machine with additional cores, it'll run that much faster, but I want you to get a feel for how the simulation runs on this kind of hardware. So what we see are 2 graphic views of our model. I'm going to maximize the windows so I can just see one of them. And you'll notice what it consists of is essentially a box containing 2 fluids. Above this green plane is air, and below the green plane is water. If I zoom into the model geometry, you can see the model has all the same level of detail that was in my Rhino model. So we haven't lost any detail about our model in this simulation. All the same appendages and features of the design are in there. So how do we decide how big this box had to be? It's not arbitrary. You can't make the box, the fluid domain representing the box, an arbitrary size. Well, this marine template that I referred to earlier made that decision. It looked at the type of model I'm running, and it looked at the speed I'm going to run and the size of the model, and it decided how big it needs to make this. Different analyses might have a different set of proportions for the fluid domain. In addition, over in this simulation tab, where you can see the simulation is running as evidenced by this icon that's moving in the simulation tab, there's information like the simulation time or duration. How long does the simulation have to run? This is running for 8 seconds. And how many time steps should I break those 8 seconds up into? 1,600 time steps. These are not arbitrary numbers. They're very important numbers. The length of your simulation, the duration, is estimated based on rules of thumb in order to figure out or get to a converged state, a steady state. And the number of time steps to subdivide your simulation up into is also not arbitrary. It's based on some calculations having to do with the relative size of the cells compared with the speed of the flow through those cells. So this has all been done for you automatically by the marine template. You'll also notice there's a field called number of iterations. What does that mean? Well, these equations that we're solving, the Navier-Stokes equations, are quite complex and quite nonlinear. So it's difficult to solve them directly or explicitly. So we have what's called an iterative solver to implicitly compute the solution. The way the iterative solver works is at each one of these time steps, it guesses at the answer for the next time step based on the result from the prior time step. After making that guess, it solves the equations associated with the Navier-Stokes system and compares the resulting state with the guess that it made and adjusts the guess for the next iteration. And it does that 5 times, trying to improve the guess at the answer each time. So what you see in this residual plot here at the bottom is a series of those iterations, 1 through 5, progressing during a single time step. If I look down on the lower right-hand corner of this window, I see the number 6 in parentheses. That it means I'm on the 6th time step out of 1,600. And the number next to 6, 0.03, says I'm at 0.03 seconds into the simulation, 300ths of a second, out of 8 seconds total. So you can see it's going to take a while to run this simulation. I believe this simulation will run in about 10 or 12 hours on my laptop. We have other machines that are faster, have more computing cores, and the answer or the simulation runs roughly proportionally
as fast with additional cores. So what it's solving is it's solving the system of equations, the Navier-Stokes equations, for this fluid volume where we've broken up the fluid volume into little subvolumes. We call those cells. So for example, if I look at this fluid domain, you can see how it's broken up the domain into smaller sub pieces of fluid called cells. So there's an example of a cell right at the corner of the fluid domain. If you look at the fluid domain at a plane cutting through the domain, so this is a plane that cuts right through the middle of the model. If I turn on the grid, you can see how it's broken up the fluid domain into smaller cells, how it also has a meshing strategy whereby it creates smaller cells in areas of the fluid flow where you expect a lot to be happening. So there's not much going on in the fluid way down in the bottom here, so the cells can be quite large, but near the vessel and behind the vessel where waves will be generated, you'll find much smaller cells because we want to capture or resolve the fluid flow with appropriate level of accuracy. Okay, so this is an example of a plane cut through the fluid volume. If you want to see how many cells are in the entire domain, you can go under the Mesh tab here. Let me make this a little bigger. Meshing tab, and go into Grid and Geometry information. And you can see right here in number of cells, that number there represents 2.4 million approximately. So there's roughly 2.4 million cells in this fluid domain, which tells you why CFD tends to be so RAM memory intensive, is because all of that information for each cell, each one of the 2.4 million cells, information like pressure, velocity, volume fraction, turbulence, turbulent energy, things like that are all held in each cell and computed in each cell for each of 2.4 million cells. So it requires a significant amount of RAM to do that. You can see already probably when I select multiple things in my view, the hull, the deck, the rudders, and the free surface, you're already starting to see a little bit of disturbance on the free surface because the boat's accelerating. In these simulations, the boat starts sitting in equilibrium with no speed at time 0 and accelerates up to your target speed and allows the fluid flow to evolve and the dynamics of the vessel to evolve till a force balance is reached. One other item in the simulation tab that we didn't talk about was the results saving frequency. What this is you remember I said all of the information for those 2.4 million cells are being held in RAM memory. Eventually, though, you want that information written to your hard drive for a persistent state in order to be able to get back to that simulation at a later time. So you don't want to have to come back on another day, open the simulation and rerun it if you've already run it once before. So what you do is you save the results in memory to what we call a results file on your hard disk. Well, this field here is the results saving frequency. It defines how many time steps go by before we save a results file. If this number was the same as the number of time steps, in this example 1600, that means we would have one results file that was saved at the end of the simulation. But you notice the number's less than the total number of time steps. And what that means is it's going to save results every 400 time steps, or in the context of this simulation, 4 times during the course of the simulation. Why do we save it more often than just at the end? Well, if you're running this simulation overnight or over the weekend, and say you lose power or your computer reboots because Microsoft sent a Windows update to your computer, if you hadn't saved any results files, you would lose everything and you'd have to come in the morning and restart from scratch. What saving a results file does is it lets you load the most recently saved results file that you had before this reboot or loss of power occurred and continue the simulation from that point. So you can continue a simulation that you've started to run by opening the results file and clicking the start button, and it'll continue by default from that point on. There's another use for result saving, and that has to do with making animations. The way our animations, and just for background purposes, if you haven't seen an animation, a CFD animation is really like a little film or a movie showing the progress or the evolution of the flow and dynamics of the model through the simulation. The way those are created is there's a command to create a simulation, and what it asks for is for you to select all the results files that were created for that simulation. And then this command goes and opens each one of those results files in chronological order, one at a time, puts the simulation in the state it was at that point in the simulation, and takes a snapshot and adds that as a frame into your animation. So the more results files you have, the nicer your animation will typically look, because it'll be smoother. This default value of 400, result saving frequency of 400, would end up giving you 4 results files, 1600 divided by 400. In the end, that would not be a very useful or interesting animation, because it would just have 4 frames in it, and it wouldn't show you very much. So you typically want a smaller number here if you're interested in doing animations. In addition to these graphic views that you can manipulate, and there's a lot of good instruction in the Orca help file for how to work in these views, both in terms of manipulating the mouse, manipulating the view camera, but also working with this window we call the geometric entities panel for selecting individual things to look at in the model. You'll notice when I select something, it highlights that or color code, false colors it in the 3D view. And if you hold your control key down, you can select multiple things. And I've just done that here in order to show this view as you see it. But the process of that is described well in the help file. So in addition to this 3D view, we also provide time history plots. So you can see by default, there are 2 plots here, plot 1 and plot 2. Plot 1 shows you the time history. So the bottom axis is time of heave motions, the blue curve plotted against the left-hand axis, and that's heave at the center of gravity, and pitch motions in red curve plotted against the right-hand axis. And there it's important to note that negative pitch is bow up. Okay, so negative pitch is always bow up. So you can see the model is moving, heaving up and pitching up, and which is exactly what you would expect in a planing hole like this, accelerating through its speed range. The second plot is resistance, the total drag of the model, both air and water added together, and what we call effective power in the red curve. So remember, because there's no propellers in this model, we're only able to get the power associated with the resistance or drag. We call that effective power. When you run a self-propelled simulation, you could get something beyond effective power. You can get the power that has to be delivered to the propellers to generate the thrust and reach the speed that the model is at. So we call that delivered power. So you can get delivered power in a self-propelled run, but in a resistance or towed run, you can only get the effective power. So how do we know when the simulation is converged? Well, we know technically it's done at 8 seconds, right? Because the Marine template chose 8 seconds, and you can see we're now 0.09 seconds of the way through that simulation, just starting 0.095 seconds. So strictly speaking, from the point of view of this time duration, we know how long the simulation has to run. But what really defines how long the simulation should run is convergence of the results. And the results are considered converged by looking at the dynamics of the vessel. So this is the pitch and heave, those are the dynamics, and waiting for those dynamics to steady out. How do we know when the pitch and heave is steady? It's steady when these plots become horizontal. So when this blue curve becomes purely horizontal, and when the red curve becomes purely horizontal, that's one indication of having reached a converged steady state. The other thing we want to look at is the drag, the integration of the forces on the model. So the resistance is a good plot for analyzing the drag behavior. And again, we want the drag to also reach a steady state or a constant value. We don't want it to be varying like you see now. So these two plots are very helpful in allowing you to determine when the simulation is converged. Now, hopefully by 8 seconds it will have converged. And usually the number that we put here is a pretty good estimate of how long you need to run it, but sometimes you may need to run it longer. So you may have to continue the simulation after the 8 seconds. Sometimes it'll finish early. When I say finish, it'll reach a converged state earlier than 8 seconds. It really just depends on the model and the conditions of the simulation that you're running. But the good news is you have a good way of examining what's happening with the simulation. As I said before, we create two plots by default, but you can create your own plot by clicking the Add XY Plot button at the top of the user interface. So when I clicked that, it just added this plot 3, which is empty by default. And as you'll see in the manual, if you read through it, I can come over to the Model tab, click Marine, and that gives me some of the variables that are available to plot in the time history. And one that we haven't looked at yet is the forward velocity. So I'm going to add the forward velocity to this plot. And one of the other nice features of the plotting portion of the user interface is that you can easily change units. They default to the SI, but if I click this plot properties button here, I can change the units to something like knots or something I'm more comfortable with. And you can see that the vessel started at 0 speed at time 0, and this is a straight line. It actually increased the speed of the model at a constant rate. So it's a constant acceleration up until 1/10 of a second, it reached 25 knots. So for the rest of the simulation, it's going to be horizontal. It's just going to stay at 25 knots. And really all we're waiting for now for the rest of the simulation is for the boat's dynamics to reach a steady condition and for the flow field to evolve. We were able to accelerate the model in a very short period of time, much shorter than would be physically realistic, right? We can't in reality accelerate this boat from 0 to 25 knots in 1/10 of a second, but we can in a CFD simulation because we have an unlimited amount of thrust that we're applying. The reason we do it so quickly is hopefully that'll help you get your steady state answer more quickly and not have to wait as long. If I accelerated it more slowly, it might look more realistic, but in the end, it'll take longer to get my steady state answer, and you'll have to wait. So you'll have to wait longer to be able to apply that information to improve your design. So even though we can accelerate the model that quickly, the model can only respond at whatever speed is realistic for that acceleration based on its inertial information, its mass properties. And similarly, the water can only respond in a certain way. So we have to wait. We can't make the water respond very quickly or the boat respond very quickly. It's really just waiting for the rest of the simulation to run. A couple of other nice features about the plotting portion of the user interface, the time history plotting. It's very easy to get around. You can use your right mouse button to zoom, to pan around. You can pick a certain part of the simulation and zoom in, drag a window to zoom with the left mouse button, and then double click to refit. So it's very easy to get around in this plot window. And it also has ways, for example, to extract information. So here's the pitch and heave window or plotting window, and there's this little yellow copy data. If I click on that button, what that does is it copies the data that was in the plot at the time I clicked the button. It copied it to the Windows clipboard. So now any tool, any application I have that's aware of and can interact with the Windows clipboard, like Excel, for example, can use this information. So I'm going to use Excel to open up a blank workbook, and I'm going to paste from the Windows clipboard into Excel, and you can see what it did is it pasted the information in terms of the time history abscissa value, the time in the simulation, and then the two ordinates, the heave, which was on the left-hand axis, and the pitch, which was on the right-hand axis. So you get all that information. So if you want to get information numerically, sort of the raw data out of the simulation, this is the way to do it. You don't have to just keep zooming in to your plot. You can actually copy it into the Windows clipboard. So with that, this simulation is going to take a while to run, as I mentioned. So what we're going to do to show you what it looks like when it converges is go to a run that I've completed on another machine here. So this is the same run shown after it's run for 8 seconds. You can see now in my plots, I'm going all the way out to 8 seconds. I'm looking at pitch and heave just like I was before, but you can see how eventually the pitch and the heave leveled out by around 6 seconds. These two values weren't changing very much. Okay, so pitch and heave sort of leveled out before the 8 seconds at around 8 seconds time. And if I look at my plot too, there's resistance. So there was some significant increase in resistance at the very beginning of the simulation since I was accelerating the model to speed. But then I'm just waiting for the flow field to evolve, the resistance to level out. And you can see if I zoom in with a narrow window here, how my resistance is more or less a constant value. It's varying a small amount, and there's a high frequency variation, which is due in part to the transient nature of the flow. It's really an unsteady flow, and to some extent numerical behaviors. But generally speaking, to say I'm getting it constant within 5 pounds out of 2,000 is pretty good. So this is where you would take your measurements out of at the end of the simulation. You can also see in this view here how the flow field is now fully evolved. It's going all the way to the back of the domain. The wave field is not changing much, it's staying virtually the same. And in this particular simulation, I added streamlines for visualization purposes. So you can always add streamlines to your model. This is a capability built into the tool, and so I've added them here. So for example, you can see how the air flows over the model, the so-called station wagon effect or recirculation zones behind where the air flow has separated. And then you also get the streamlines on the water side. So you can see how that flow is evolving too. And another view, the second view, which I didn't focus too much on earlier, but here will be usually quite interesting to look at, is the overhead view of what we call the volume fraction. So what this shows is the intersection of the free surface with the hull. So everything that's blue, color-coded blue, is all air, all in contact with air. Everything that's this magenta color is in contact with water. And then at the interface, you'll see these changes in colors according to this color bar over here. So that green is right in the middle. And what the green means is those are portions of the model that are mixed air and water, 50% air, 50% water, equally mixed. So it gives you a good view of what the flow pattern looks like on the bottom, where the spray route and stagnation lines are. You can also see quite clearly how this lifting straight, some might call it a spray rail, is doing a very effective job not only of deflecting spray, but keeping water from staying attached to the hull, and presumably reducing at least the frictional component of drag. So you can look at this from various angles, but that's really what that view is showing you. What you see here is a little bit of air getting entrained just outboard. There's separated flow there, and so there's a little bit of air getting entrained in there. I don't know if I could zoom in and you could see it, but it is occurring there. So that's the final view, and you can extract a lot of different data out of this view depending on what it is you're trying to get. Like I said, streamlines, drag, the steady state heave and pitch. So this model reached a steady state trim, or what we call pitch, of about 3.1 degrees. Okay, so it's important to recognize that this pitch angle is above and beyond the static trim. So if this model was sitting with 0 trim in Rhino, but when you floated it, it had 1 degree, say plus 1 degree of trim, meaning the bow was down 1 degree, and now it's saying a bow up trim of 3.1 degrees, you would have to add the two in order to figure out the net change in trim. So this is dynamic trim, is what we call pitch. So that's an overview of how the process runs. One other thing I want to show you is back in Rhino, there is a functionality to do some reporting in Orca and Rhino. You can extract raw data out of the Samaric CFD simulation through that plot clipboard copying approach, but there's a command that allows you to report across speeds called create CFD report here. And the way this command works is you point to the folder. Remember, you had to specify that folder where you were going to generate your files. I've used this folder here to generate results from a series of run, and it automatically looks in that folder and all child folders, all descendants beneath that, and finds any other results that may have been generated. And you can see by default, the command creates subfolders for each speed. Now I have some in here that seem to not follow the naming pattern, and that's because they were done for different purposes. So I'm going to deselect them and only include the checked ones in the analysis. But when you click on create report, what it does is it first of all uses Excel for its reporting, because people like to work in Excel. It's easy to use. If you want to do some customization to the report after it's been generated, you can easily do that, change your plot characteristics, things like that. But what it's doing now is it's loading the results from each of those runs at those different speeds that I pointed out earlier when I ran the command, and it's generating a summary report of all the results. So you're going to see a table of results in a moment that is a summary of all the results files that it was able to read, and then it will also generate some graphic information showing plots of the information. So here's the tabular results I was referring to. First, you get a little list of characteristics of your design, just so you can figure out what displacement did I run this for, where was my LCG, etc. But then after those characteristics, it shows a table as a function of speed. So here's my speeds. It shows you the computed heave, pitch, and resistance, which is what we were looking at earlier in those graphs in the Samaric MP program. So it shows you heave as a function of speed, how it varies. This is steady state heave, right? So this is the heave value that the model reached at steady state. This is the pitch value it reached at steady state, and then the resistance. It also has a number of other columns where, if you wanted to, you could add additional components to your performance prediction that maybe weren't included in your CFD analysis. For example, things like hull roughness, if you wanted to account for, a fouled hull or just a naturally rough hull. Margin. Some people have margins that they add to their predictions, especially early in the design when things are still changing. So I can come over to this green field here that says margin, currently 0, and I can say, let's say I want to add a 5% margin. So I make that 0.05, and what it'll go ahead and do is compute a 5% margin and add that into the total. So now the total is the raw data from the CFD along with the margin. Okay, so that's how this works out. Remember, this is effective power, doesn't include any propeller efficiency. In addition to this tabular information, I can go to the resistance tab where I can see plots of information. And this is, again, showing the variation of different things with speed. So the blue circles are the raw CFD resistance that came out of these simulations. Now I've had to run these for all these speeds, right? What I'm running now for you is just a single speed. This is a result of having run multiple simulations over this range of speeds. Okay, so this would take several days to do, depending on the hardware you're using. The orange is the total resistance. What's the difference? In this case, I just added 5% margin. So the orange is just 5% above the blue. And then the effective power is shown in these gray diamond shapes. So useful information to see how things vary with speed. I can also plot my heave and pitch. So for example, the blue circles are the heave as a function of speed, the steady state heave, and the orange squares are the steady state pitch as a function of speed. Remembering again, the negative pitch is bow up. So it looks like the highest trim angle or pitch angle that this would run at was about 3.1 degrees bow up. Again, that's relative to the static equilibrium starting condition. And then after that point, higher speeds resulted in lower steady state running trim angles. So a useful tool just for reporting across multiple speeds in your simulation. Okay, so that's really most of what I wanted to cover. There's a lot of information I could add. One thing that I should at least mention here in passing, going back to my CFD input dialog, there's an options tab that has useful information, but one thing in particular that you should examine is the CFD grid size. This control allows you to control globally the size of the cells that are generated for the CFD simulation. Typically, smaller cells might result in more accurate predictions from the CFD, but also it takes longer to run. So it's really all about finding a balance of runtime and cell size. And we've set normal to be the default that we hope will give you good answers for making design decisions. But the way you can know that for sure is you pick one speed, your design speed, and you run the same simulation, same speed, with 3 different mesh levels, say normal, medium, fine, and fine, and you compare the results from those 3 runs at the same speed. And what you hope to find is that there's not much change in the results. What that would indicate then is that your normal, in this case, the lowest mesh setting that you would have looked at of those 3 would be adequate to do for the rest of the analyses. But if you find that there's a big difference between normal, medium, fine, and fine, that may indicate that normal is not a satisfactorily dense enough mesh in order to accurately perform your analysis, and you might consider going to a finer mesh for all of your rest of your runs. So we call that mesh convergence study or grid convergence study, and we always recommend that you do that because normal we found to be good for the vast majority of cases, but everybody has slight differences in the design, and we never know if there's something in terms of fluid flow phenomena that might require a finer resolution of the grid to accurately predict.